In this detail video, I'd like to prove a technical lemma. And this is a little lemma which comes up all the time. It's kind of an important thing to know. So the statement is as follows. Let's let U be an open set in some space X, and let's let S be a sieve on U. And when we say this, we really mean it. We're not regarding S as a covering sieve necessarily, just any sieve. So S is any sieve on U, and F is any presheaf on X. So then the set of functor morphisms from S to F is equivalent to, or is isomorphic to, or is in bijection with, whichever you prefer, the inverse limit over the sets V and S of the F of V. And as I kind of said outside of the box here, for the left side of this to make sense, you really need to be thinking in the external perspective, and for the right side of this to make sense, you should be thinking in the internal perspective. So we use the external perspective on sieves and then the internal perspective on sieves. And this isomorphism is an important one, and sort of comes up all of the time. Alright, so let's prove it. And this is one of those things where if you kind of remember the definitions, or if you unfold the definitions, this statement almost becomes a tautology. So let's start by remembering the definitions, and then we'll describe the translation, the way of kind of exhibiting that isomorphism. So what is Hom and O of X between S and F? Well, that's the set of functor morphisms maybe which we'll call alpha from S into F. And remember, so functor morphism alpha is a collection. I'm probably going into too much detail here, but alpha is really a collection, say alpha of U, for every U inside of O of X, of maps from S of U into F of U. This is what alpha U is. And then these maps are required to satisfy a certain naturality condition, so such that, well, maybe I'll keep the same color, such that whenever we have some inclusion W inside of U, the diagram S of U down along restriction to S of W across, this is alpha U, alpha W, F of U, F of W, and these are the restriction maps. So this is the restriction W inside of U, such that whenever we have this, that diagram commutes. Okay, so that's remembering what this guy is. And on the other hand, what is this inverse limit of all sets V inside of S of the F of V? Well, that's equal to, I guess I like to think of it as being the set of matching families, or coherent families, or coherent sequences, whatever you want to call it. Matching families, we'll call them S of V, V inside of S, yeah, those matching families. And what does that mean? Well, a matching family, yeah, so I guess I should say SV is such that, this is what it means to be a matching family, is such that whenever W is inside of V, we have that SW is equal to the restriction W inside of V of SV. So maybe just to be perfectly clear here, SV is inside of f of v. That's what's going on when I say this. Okay, so these are where the two things are. And now let's see why they're isomorphic. So why don't I do this just by giving a map going from here over to here, and then I'll give an inverse map going from here over to here. So in both cases it isn't hard to guess what's going on. But let me think, which one will maybe be nicest to do first? I think this one. So, okay, let's describe that map. So we want to get a map. We want to get a map from this guy over into Hom O of x hat S into F. Okay, so if we have some family over here, if we have some coherent sequence, what we're going to do is map it to the functor morphism, S from alpha into S, where, maybe I should, well, too late now, I'll just draw this down like this. So the functor morphism alpha, where if, I guess, V is not inside of S, then alpha of V is just the only possible map from the empty set into F of V. And if V is inside of S, then S of V is equal to the single point set, and alpha of V is the map which takes that single element and takes it to S of V in F of V. So that's what the map is in this direction. And we could wonder whether this is actually natural. And it will be, right? So why is it going to be natural? So we only have to check the case where, say, V is inside of V prime, which is in S, right? We only have to check naturality when we have two open sets, both of which are in the sieve, because if the top one isn't in, well, so if the top one isn't in the sieve, then there's no naturality thing to check, and if the bottom one isn't inside of the sieve, then the top one isn't either by the downwards closure condition on sieves. So we only have to check it in the case where we have two open sets, both of which are inside of the sieve. And their naturality, well, what's going on? We have S of V prime, which is equal to a single point set, and S of V, which is equal to another single point set. And the restriction map in this case is the identity over on this side. I don't know why I drew these as inclusions over here. They really, I mean, I guess they are, but it's kind of not important. Maybe I'll stop doing that. But here we're going to have alpha V, or alpha V prime, and this is the map which takes star into SV prime. And down here we'll have alpha V, and this is going to take star into S of V. And we have F of V prime up here and F of V down here. And this is the restriction of V inside of V prime. So the naturality condition boils down to asking whether it's true that S of V is equal to the restriction of V inside of V prime of S of V prime. That's what the naturality condition boils down to. So let me briefly review kind of why we're doing all of this. I gave this alleged map, right? I told you how to take this family over here, to take an element in this set, and turn it into a purported element in this set, to this thing alpha defined as follows. And alpha is a collection of maps, but maybe it's not natural, right? So we have to check that it's a natural transformation, that it's an actual functor morphism, that it satisfies this naturality square condition here. That's what we're trying to check. And we've seen that checking whether that's true boils down to answering this question. Is it true that S of v is equal to the restriction of S of v prime whenever we have v and v prime inside of the sieve? And that's true, right? That was exactly this matching condition that we had up here. So this map is indeed well defined. Okay, and I think that's all that I want to say about this map from the inverse limit into the Hom set. So now let's go in the opposite direction. I'll go over here instead. So now we want to define a map set of S, f of v. We want to be going from the Hom set into here. Hom O of x hat S f. Okay, so it's not hard to guess what this is going to be. So let's let A be inside of here. Let's let alpha be inside of here. So alpha is a natural transformation from S to F, and we want to define a matching family. So what are we going to do? We're going to map this to a family consisting of alpha of star, alpha v of star, for v inside of S. So remember, alpha is a collection of maps from S of u into, well, I guess I shouldn't be using the letter u because we've already kind of used it when talking about the covering sieve itself. But alpha is going to be a map, or a collection of maps, alpha w, from these things into f of w. So that's what I mean by writing alpha v over here. I'm referring to the map from S of v along alpha v into f of v. That's what I mean by this alpha v over here. So we take that natural transformation, we take that functor morphism alpha, and we map it into this family. And now we can ask ourselves, well, does this family match? Right? Is it true? Is it true that alpha of v is equal to the restriction of v inside of v prime of, is it true that alpha v star is equal to restriction alpha v prime star when v is inside of v prime? But that is indeed true, because that's just asking whether this map commutes, or this is the identity, and this is star maps to alpha v prime of star inside of f of v prime, and this is the map star maps to alpha v of star in f of v, and this is the restriction of v inside of v prime. And does this commute? Sure, because this is exactly the naturality condition over here, because this is equal to s of v prime, and this is equal to s of v. So this map is also well defined. Okay, so at this point we have produced well-defined maps in this direction and in this direction, and I claim that it's obvious that they are inverse to one another. And I'm going to end the video here.